This first example of optimizing a quadratic function is a real classic, and it probably appears in most books, but I like to talk you through it, and particularly because some years ago, one of my former college algebra students came back and told me that he was working at a lumber yard when a customer came to a counter and actually asked him a question like this. And since he had already done the problem, he stepped up and figured it out for the customer. So we had a great laugh out of it because this really was a real-world problem right here in our area. So anyway, here's the problem as I stated it. A farmer with 2,000 feet of fencing wants to create a rectangular pen with one side open since it borders on a creek. What dimensions will give him the largest area? All right, so there's a creek on one side, and the cattle won't cross it, so he doesn't need to fence that in, but the pen will have three sides, and is made with 2,000 feet. So how should we construct this? Use that 2,000 feet in order to create the largest grazing area. Well, with 2,000 feet, we have two sides, which I'll call X, and this side, let's call that Y. And so the area, already we know what that is. The area would be X times Y, wouldn't it? Length times width. But in order to maximize the area or optimize the area, we need to turn this function into a function of a single variable. Now that you studied in a previous section on math modeling, and where we took physical situations and turned them into functions of a single variable. So we're going one step further with that process now. And let's see. Well, we know that these three sides must add up to 2,000 feet. So I've got 2x plus y equals to 2,000. And if I solve for y would be 2,000 minus 2x. And I'll write that here also. So now I have an alternate function for the area. This length times width. So in essence, I can replace y with 2,000 minus 2x. And that gives me area equal to x times 2,000 minus 2x. So I've created a function, and we could call that a of x if we wanted to, and a function of a single variable. Now I'm going to make some room up here, erase this, and finish the problem. All right, I rewrote our quadratic function up here, and how do we know that's a quadratic function? Because if I multiply this out, and I'll write it in descending powers, I would have minus 2x squared, and then plus 2,000x. So that's a quadratic function. And how is it pointed? Well, it's pointed down because of the negative leading coefficient. So it loops over, which means I have a maximum at the vertex. Maximum what? Well, it's the maximum area. So take a look at how this graph looks like. And I'll try to squeeze it in over here. Here's x, and here's area, a of x. If I plot those against one another, when x is 0, when a of 0, x is 0, I've got 0 times 2,000, that's still 0. I have 0 area. Now that makes sense, because if my rectangle has no width, in other words, it'd be just like laying out 2,000 feet along the creek, you wouldn't have a rectangle, would you? So the area would be 0. And then at the other extreme, if the x was equal to 1,000, what would happen? Well, if I plugged 1,000 in, I would have 1,000 times 2,000 minus 2,000. 1,000 times 0 would be 0. So in other words, the roots of this function are at 0 and 1,000. And 1,000 would be what happened if you laid out 1,000 feet this way and then used the other 1,000 feet for that side. you would have nothing left for this length. In other words, you wouldn't have a rectangle there either. You would have 0 area. Being a quadratic function, it's a parabola, goes up, comes down, and it does go down this way, but our problem can only exist between 0 and 1,000. Our domain is restricted between 0 and 1,000 because we can't have a negative number of feet for x. We can't have more than 1,000 feet for x. And so I'm really only looking at between those 2 points. So where is the vertex on this? It would be exactly in the middle, wouldn't it? Right there. What is that number? It's a little crowded here, but it's 500. So when x is 500, I should have the maximum area. And if I plug 500 in here, 2,000 minus 1,000 is 1,000. And indeed, these 3 numbers add up to 2,000. So that should be the maximum. Now I realize you can also use that little formula, x equals minus b over 2a, in order to find the vertex for this. So you can proceed to use x equals minus b over 2a, find the vertex that way if you prefer. I wanted to show you the picture though, and of this problem, because here's the area. Where is the maximum area? It's at the top of the curve, which is the vertex. And where is the vertex? It's immediately right in the middle between these 2 roots because of the symmetry. Alright, so let's, I need to write an answer so we can finish the problem. But this really is a classic college algebra problem. And but I always liked it, especially when I found out my student actually got this question one day at a lumber yard. Alright, so the area is maximum at, what is the area? X is 500. It was 500 times 1,000 when I erased my picture, but I think it was 500, 1,000, and 500. So 500 times 1,000 would be 5 followed by 5 zeros. 500,000 square feet. At 500,000 square feet, oh, that would be probably a good 12 acres maybe, give or take. Area is maximum at about 500,000 square feet using dimensions of 500 feet. Whoops. Let me get my feet in there. Times 1,000 feet. There we go. So dimensions are 500 feet times 1,000 feet. In other words, it's twice as wide as it is tall, and there's the maximum area. All right. Well, let's go on and do a different problem here.